Okay, so we have this idea of an ordered pair. This is just for the video. And then we can talk about a relation as being a set of ordered pairs, and that set may be generated based upon a rule. Then we have, don't worry about writing all of this down, just this on the top right-hand corner here. Then we have this idea of a function. And I'm pretty confident you all have heard of a function before. Yeah? Okay, so a function is a relation. A function is a special kind of relation. If you think about it, the functions that you're used to, like y equals x squared, it's the same idea. It's a relation. It generates a set of ordered pairs, and those ordered pairs are often according to a rule, like f of x equals x squared. Okay, that is a relation. So you've got up here at the top there then a relation. A function is a relation such that each x value has only one corresponding y value. And I'm going to explain it to you in a moment, but can you at least write that bit down for me? Zoom up just for this bit too. Okay, so a function, so all functions are relations, but not all relations are functions. What makes a function is this idea here, that if I have an x value, it will only correspond to a single y value. If it corresponds to more than one y value, then it doesn't exist. And I've got here x squared plus y squared equals 1, a bit similar to the example I did on the board before I was doing the video. So if I substitute, this is a non-example. So if I substitute the value -1 and solve, I'd get -1 squared here, which would be 1. And then if I subtract 1 from both sides, I would get 0. So y squared equals 0, and that means that y is equal to 0. Is that okay? Okay, what about the number 0? Well, let's do 1 first, actually. If I do 1 here, 1 squared is equal to 1. Subtract 1 from both sides, I get 0. The square root of 0 is 0. I'm going to get the 0 as well. That's fine. The fact that I've got two inputs here, or two x values going to the same y value, is absolutely fine. That by itself does not stop it from being a function. Okay, so you can go from multiple x values to a single y value. That's fine. But let's have a look at 0 will do. At 0. So 0 is now the value of x. 0 squared is 0. So I've got y squared is equal to 1. If y squared is equal to 1, what does y equal? What's the square root of 1? But that's not the full story, right? Because it actually equals plus or minus 1. Yep. Frozen? So we can see here that when x equals 0 or x equals a half, the output is two possible values. And so therefore, we can say that the function is a relation, but it is not a function. It's a relation, but it's not a function. If I go back to Desmos, I'll just make it x squared plus y squared equals 1. Teeny tiny circle. We can see that it's graphable. Nothing wrong with the graph. We can see that it would produce a set of ordered pairs, lots of xy coordinates, everything from 1, 1 to -1, 1, 0 to -1, 0, 0, -1, 0, 1. All of these are possible values. They can form a set of ordered pairs, so it's a relation, but it is not a function, okay? Because when I have a look at it, if I go, say, here, the value of, say, a half, which is roughly here, has one value here, but also one value here. So it's got two possibilities that come out of it, and therefore it is not a function. It is only a relation. We okay with that? Okay. I'm just going to front end with a little bit of theory before I get you to do some work about this. So the next two key words that you need to be aware of is domain and range. I'll give you a chance to write it down. So the domain is the set of all x values, all the values that are possibly able to be put into the function. Often that set of x values is basically any old number you want to, but it's not always. It's not always, but it can frequently be any old number you want to. The range tends to be more interesting earlier on. So the range is the set of y values of a relation. Okay, so we can talk about domain and range of a function, or domain and range of a relation, because all functions are relations. So I kind of have this thing that I use, which you may think is too silly, I don't know, but I have this little aid to memory. The domain is the set of all input values, and we call that the x coordinates. The range is the set of all output values, and it is usually the y values. So there's a little aid to memory called Dixroy. So Dixroy means the domain is the input values, it's the x coordinates. The range is the output values, it's the y coordinates. I'm going to switch over to Desmos just to sort of give you an example of what I mean with this domain and range. Just trying to think what your experience is so far. Okay, I think we've all seen quadratics, haven't we? So if I create a function y equals x plus 2 all squared minus 3, the domain for this function here, I'll just zoom out a bit, is, well, every single x value that I can think of would be able to be input into the function. In other words, if I put a value in, like minus 5, I will eventually get to the blue line. And then if I get to the blue line and go across, that would be the output value, right? That'll be the y coordinate. Okay? Now, you could think of minus 25 and go, well, minus 25 is not going to touch the graph, but it does. We just got to zoom out more. And then minus 25, which is about here, is all the way up here somewhere. But we can get to the blue line, given that that blue line goes on forever. So the domain, the way we would say this is the domain is all real values. And I'll show you how to write that down in a second. I'll zoom in a bit. The range, however, is a little bit more interesting. The range is not all real values, right? So, for example, the value minus 4 here is not part of the range. There is no value that you can input into the function and get minus 4 out. It completely misses the graph. In fact, if I go below minus 3 at all, it'll be a value that's not within the range. The other side's not true. Doesn't matter how far I zoom out. If I go up here somewhere, like this is now up to, there's 1,000, so this is what, 2,000 up here. I'm going to hit the blue line left and right here and here. So I definitely would get an output of 2,000. I'll definitely get an output of 1,000. I'll definitely get an output of, I don't know, 0.5. I'll definitely get an output for all of those sorts of things. I'll continue to get outputs, except I won't get any outputs that are below minus 3. So the range for this would be from minus 3 to infinity. Is that making sense? I'll do a really brief example of a graph that doesn't have a full input. Y equals, how about the square root of x? That'll do. There we go. This is the graph of y equals root x. Everything from 0 onwards, input. Everything from 0 onwards is an acceptable input. The square root of 0 is 0. The square root of 4 is 2, and so on. All of these are legitimate. But as soon as I try to square root a negative number, the square root of a negative number, you should know, doesn't exist, right? There is no number that I can square and get -2, for example. It doesn't exist in the real set, if you want to be more precise. So that means that the domain for y equals square root of x is all real positive numbers plus 0. So from 0 to infinity. So that's an example of where the domain might not be just any old number that you want. What do you think? There's more and more examples that we'll come across as we go through it, but this is just just to give you a bit of illustration of what's going on. So in slide 4 here, I've got notation, and you can write that down. I've got a bit more to say about that. So there's a couple of notations that we can use, but when we are trying to describe a function in terms of its domain and its rule, this is the notation we use. We go, f is defined as going from a domain to a range, or the domain maps to the range. Domain maps to a range. In other words, there is a coordinate in the domain or a value in the domain that has a corresponding value in the range. So D maps to the range. Now, I'm going to pause the video and do a little bit of board work. So the way we can write this is using this symbol here called, it's lowercase epsilon in Greek. And we say is a member of or belongs to. So X belongs to the domain, Y belongs to the range. That's all it means. And an example of that, now this is where I'm not too sure how much knowledge you have coming into the course. So I'm going to write it, but then I'll discuss it. I can write, wrong color. X belongs to that. Now I'm going to pause there for a second. Who is familiar with that notation I've just done? This bit here. Yeah. Anyone else? Yep. Yep. There's at least a couple of hands down. Does anyone feel brave enough to explain what that means? Yeah. Continuously, yep. To infinity, yep. That makes sense to people, I hope. Florence, can you also remember what a square bracket means? Yep. Eve, can you? Yep, nice. There is that. I could have written this though. That does not mean the coordinates 1 and infinity. That also means all numbers between 1 and infinity. But the difference between this one and this one, do you remember, Miles? The second one's closer. But what does the round bracket here mean? Yeah, I can see. You're almost there, though. You've basically got the bones of it. A square bracket means that number is included in that set. So it means everything from and including 1 to infinity. And then if it's a round bracket like this, it means everything from 1 but not including 1 to infinity. Yeah? Does that ring a bell? No, but anyway, I've said it now anyway. The reason why we have a round bracket for infinity is not so much that infinity isn't a number, but that is true. It's that we can't reach infinity. So infinity isn't a value we can plug in, but it means everything from there onwards kind of thing. Infinity is a concept. It's not really a number. And you can raise that with your top teacher if you like. Please explain why infinity is not a number. Why is it just a concept? Okay, so that's what that notation means. That means from 1 to infinity, but not including. I'm going to raise that because I just want to keep it a bit cleaner, but I'll do another example underneath. So another example is y is a member of comma 1 to 1. So what that means is not the coordinates -1, 1. It means that y can be every value from -1 to 1, but these two numbers are not included in that set. Why do we do that? Why don't we just say I'll use this as an example because it's easier. Why don't we just say 2 comma infinity if we were using round brackets? Like if I don't want to include 1, why wouldn't I just go 2 comma infinity? Excellent. You're on fire today. Yep. So by using a round bracket, that includes everything from 0.999 minus 0.9999999999999999999 and even more nines, but not an infinite number of nines onwards. Okay, so that's good. Well done. So round bracket simply means it's just the end value that's not included. Square bracket means the end value is included. Okay, that will not be written down. If you need to write a note to yourself, please do that. There's also another notation that you might use as well, and I will break this down as we go as well. I'll just show you how to write those 2 symbols. It's an R with an extra bar like that. I'll even zoom up so you can see it. Okay, so I'll do that again. To draw that R, we go R and then an extra bar, not quite as wide apart as I've just done, and then you do the rest of the R like that. The Z is the same sort of thing. I just do a Z and then I do an extra bar like that. So that's how you write them, and this is what it means. Oops, I'll keep it like that. I should write the word set there, but this is the set of real numbers. This is the set of integers. Now, there's lots and lots of different notations that I'll show you in a second, but effectively, those are 2 really common ones, particularly the top one there. So if you needed to say that x can only be an integer, you could say that, use that Z there. The R there with an extra bar would mean all real numbers. Now, just a very brief word on where this comes from. Both of them come from German, and I can't remember what German for whole number is, but it starts with Z, I'll tell you that much. What happened was that if we were doing typed text, we would use bold. So bold R would mean all real numbers, bold Z would mean all integers. But then because mathematicians do a lot of handwriting, you can't really, I mean, if you just did this, it's tedious. Plus, it's not necessarily that clear to read what you're doing. And if you only do it a little bit, was that just like a thick R, or is it actually you're saying the real set? So what they did to sort of compensate for that is that they put an extra bar on one part of the letter, just so you can see that means real, that means integer. And then ironically, I suppose, I don't know if ironic's the right word to use, because this became such a common notation, then computer programs, mathematical computer programs, mathematical writing programs, started to implement using an R with an extra bar in it as well, so that you can actually write that onto your screen rather than just using a bold R. It's a bit weird. Anyway, so that's set notation. So what I could do is if I wanted to say take this function here, one that I don't know if anyone's seen this kind of function before, but if you haven't, just let me know. Has anyone seen that kind of function before? Everyone should be, this is to see who's actually paying attention. Everyone should be nodding their heads, because this is just a linear function. Every single x value is allowable here, and it will map to every single possible y value here. So the way I could write that, and you don't have to write this yourself, this is just to try and illustrate an example. The way I could write that is I could say that function, I'll do it out in this space here, but don't write it down. That function goes from all real values in the domain to all real values in the range. All possible numbers that you can think of will map to some possible number in the range. So it goes from real to real. Okay, questions? Okay, cool. All right, moving on. I've gone a bit slow. So, you know what? I'm going to skip a little bit. This bit about restricted, we're going to come back to this. Don't worry about restricted domain. So, really quickly, how can we tell if a function how can we tell if a relation is in fact a function? So, if you can, as it says here, if you can show that a relation has more than one output for a given input, it's not a function. This can be done algebraically and graphically. So quickly pop that down. I know you guys are falling asleep. I should have probably not done the stuff on domain and range yet. That's my bad. I should have got you into practical work already. However, it's more common not to do it algebraically, but graphically. So we have this thing called the vertical line test. I'll leave it zoomed out so you can see it. If you can draw a vertical line and it hits the graph, i.e. the line that you've made, I didn't want to use the word line again, and it hits the graph more than once, it fails the vertical line test and is a relation but not a function. Okay, it's a relation but not a function. And again, you only need to disprove it once. It doesn't matter that it might be okay for part of it. If it disproves anywhere, then it is a relation but not a function. So the example I've got there is a nice little curvy line there. Now, if I draw a line in, oh man, Richard, come on. Like so, that's a vertical line. That's hitting the line. I better not use that actually. I shall use range. That's hitting the line here, here, and here through a vertical line. Therefore, it fails the vertical line test. It doesn't mean it's not a relation. It's still a relation, not a function. Therefore, relation, but not a function. Oh man, sorry about the writing there. Is that okay? So, question? Yeah, the blue line? No idea. I just squiggled a line on. Yeah, there may be something out there that works. It's almost a cubic. You had to ask, and you now I have to do it. So if I go, it's a good question. Don't get me wrong. If I went, no, I don't even think this will work. Y equals x to the power of a third. Oops, a third. Nearly there, isn't it? But not quite. Yeah, I'd have to think about it a bit more. But you definitely can. You could get it with a function, of course. I just made it up. Good question. Moving back though. I just wanted to very, very quickly say that we can see here, right, nice and clearly, I hope, that I'll make it a bit bigger. Oops. That is a relation but not a function because I can draw a vertical line down here or here. It doesn't matter that there's only a single point there. It doesn't matter that there's a single point there. The point is that anywhere else, it fails the vertical line test. And as soon as it fails somewhere, it is a relation but not a function. Questions? Okie dokie. One more. This, and Iris, don't ask me what that stands for either because I don't know, is the Loch Ness. No, it's not. It is just a random function. It's a 1, 2, 3, 4. It is a power of 5 function. I can tell you that much. It is a function because it does. I can't even do it. It doesn't matter where I go down here. there is no vertical line that I can draw that will hit that blue line more than once. Okay, so I will illustrate it like this. I'm just drawing random lines here. Only hits the line, only hits the blue line once. So therefore, a function. Oh man. Okay, what do you think? Okay, I overtalked that one. Sorry, I meant to go a bit faster. So I want you to now go to your textbook, your black textbook, exercise 3A, and what you're doing is you're exploring different properties of relations and functions, trying to determine whether it's a relation or a function. So the more you can do, the better. They should be fairly quick to do. Maybe don't draw the graphs in that are there. Just look at the graphs and write relation or function or whatever else.